Glittering star clusters are not the peaceful cosmic families we once believed. These ancient, dense groups of stars hold secrets that defy the very laws of physics as we know them. By the end of this journey, you will see the universe through a completely new lens as we uncover 30 bizarre discoveries hidden within these stellar cities. We will confront stars that should not exist and black holes that remain stubbornly invisible. What does it truly mean to look into the oldest corners of our galaxy and find them alive with mystery? Deep within the dense core of a globular cluster, a cosmic predator lurks. This is the Black Widow pulsar, a rapidly spinning neutron star that is methodically devouring its stellar companion. Like its namesake spider, this pulsar is engaged in a lethal dance, blasting its partner with such intense radiation and particle winds that it is slowly, inexorably being stripped away. The energy released in this violent process creates a brilliant and deadly glow of gamma rays, the most powerful form of light in the universe. This bizarre system defies everything we thought we knew about how stars behave in these ancient neighborhoods. We assumed star clusters were stable communities where stellar lives played out in predictable ways. But the Black Widow pulsar presents a stark contradiction, a violently unstable relationship thriving in one of the most crowded and seemingly ordered places in the galaxy. Its very existence forces us to rewrite our models of stellar evolution, proving that even in the oldest corners of space, chaos is alive and well. What other monsters are hiding in these glittering stellar cities waiting to be found? The violence of the Black Widow pulsar is not the only anomaly rewriting our stellar textbooks. Within the same densely packed and ancient globular clusters, astronomers have found something even more fragile surviving against all odds: planets. This discovery is like finding a delicate dandelion thriving in the heart of a nuclear reactor. The environment inside a globular cluster is a chaotic nightmare for planet formation. Stars are crammed so close together that their gravitational pulls constantly jostle and disrupt the swirling disks of gas and dust where planets are born. Intense radiation from thousands of neighboring stars scorches everything, threatening to strip away atmospheres and boil away any potential for life. Yet somehow planets are there. Some are rogue worlds untethered to any star, drifting through the darkness as frozen, lonely nomads. Others cling to their host stars in tight, desperate orbits. How did they form in such a hostile nursery, and how do they endure the constant stellar bombardment? Their very existence defies every model we have for how planetary systems come to be. These hardy worlds suggest that planet formation is not a delicate process reserved for quiet cosmic suburbs, but a stubborn, universal force that can take root even in the most unforgiving corners of the galaxy. If planets can survive here, then where else in the universe might they be hiding? The survival of planets in such chaos is startling, but it pales before an even deeper cosmic riddle. For decades, astronomers have been confronted by a finding so bizarre it seems to break reality itself. Some of the oldest globular clusters, when dated using our most reliable stellar clocks, appear to be older than the universe. This is the Great Globular Cluster Age Paradox, a mathematical impossibility that has haunted cosmology. The method for dating these clusters is based on a simple, elegant idea. We observe the point in a cluster's color magnitude diagram where stars are exhausting the hydrogen in their cores and beginning to die, a stage called the main sequence turnoff. The location of this turnoff directly reveals the cluster's age. For many globular clusters, this calculation yields ages of around 13 billion years. The problem is, our most precise measurements of the cosmic microwave background radiation, the afterglow of the Big Bang, tell us the universe itself is only about 13.8 billion years old. This leaves an impossibly narrow window of just a few 100 million years for the first stars to form, explode, and then for these incredibly dense, complex clusters to assemble from their ashes. It is like finding a magnificent, ancient castle and carbon dating its timbers to a time before humans even learned to use fire. How can a structure be older than the material it is built from? The resolution to this paradox is forcing a profound re-examination of our most fundamental assumptions. Some scientists propose our measurement of the Hubble constant, which defines the expansion rate of the universe, is subtly wrong. A slight adjustment could add just enough time to the cosmic calendar to accommodate these ancient clusters. Others suggest we may not fully understand the internal physics of the very first stars. Perhaps they burned their fuel in ways we have not yet accounted for, making them appear older than they truly are. The most thrilling possibility is that this paradox is a direct clue, a signpost pointing toward new physics beyond our current models. It hints that our understanding of gravity, dark energy, or the very first moments of creation is incomplete. These clusters, then, are not just collections of stars. They are cosmic hourglasses, and the sand within them is telling us a story we are only just beginning to understand. If our clocks are wrong, what other fundamental truths about the cosmos might be waiting to be rewritten? This age paradox is not the only way these clusters defy expectations. Look deeper into the ancient light of a globular cluster, and you will find stars that simply should not be there. They are called blue stragglers, and they are the ultimate cosmic rule breakers. In a neighborhood of elderly, red, dying stars, these stars stand out like rebellious teenagers, shining with a brilliant, hot blue light that signifies youth and vigor. Their very color tells us they are massive and should have burned through their fuel and died billions of years ago. Yet here they are, shining brightly in a stellar old age home. How can a star be young in a city that is ancient? The answer lies in the violent, crowded nature of the cluster itself. One leading theory is that of stellar collisions. In the dense core, stars can swing so close to one another that they literally crash together and merge. Two older, slower burning stars can combine into a single, more massive and hotter star, effectively hitting the reset button on their lives. This newly forged star appears blue and youthful, a phoenix born from a violent stellar union. Another possibility involves a more insidious process in a binary star system. One star, as it ages, begins to swell. Its companion, a dense stellar corpse like a white dwarf, can then gravitationally siphon material from the bloated star onto itself. This stolen mass rejuvenates the receiving star, making it hotter, brighter, and bluer, while the donor star is left as a stripped-down remnant. These blue stragglers are not a flaw in our observations. They are a direct consequence of the extreme social dynamics within a star cluster. They are stellar vampires and cosmic mergers, proof that in these crowded cities, stars can cheat death and reclaim their youth through violent encounters. If stars can be reborn in this way, what other secrets of cosmic longevity are hidden within these ancient assemblies? The youthful defiance of blue stragglers is just one piece of a much larger gravitational puzzle. At the very heart of these ancient clusters, astronomers are hunting for a cosmic phantom, a missing link in the black hole family tree. These are the intermediate mass black holes, and their elusive nature is one of the greatest mysteries in modern astrophysics. We know about stellar mass black holes, the remnants of giant collapsed stars, and we know about the supermassive monsters that lurk in the centers of galaxies. But the space between them, a gap spanning from a few hundred to a few 100,000 solar masses, remains largely empty. Globular clusters with their deep gravitational wells and immense stellar density are the perfect places to find these missing middleweights. The search hinges on two key lines of evidence. The first is the frantic speed of stars orbiting the cluster's core. Just as you can deduce a planet's mass by watching its moon's orbit, astronomers measure the velocities of stars whipping around a cluster's center. In many clusters, these stars are moving far too quickly to be held by the combined gravity of all the visible stars alone. Something massive and utterly dark must be anchoring them, an invisible gravitational anchor. The second clue comes from brief, brilliant flares of X-ray light. Occasionally, a star or a cloud of gas will wander too close to a black hole's event horizon. As it's torn apart, the material heats to millions of degrees and screams out in X-rays before vanishing into silence. Detecting these telltale X-ray bursts from the precise center of a globular cluster is like seeing a single lightning flash in a specific, shadowy valley, strongly suggesting a powerful source of gravity lies within. Yet, for all this compelling evidence, a confirmed discovery remains just out of reach. The data is often ambiguous. The fast-moving stars could potentially be explained by a tight knot of neutron stars or white dwarfs, though that seems increasingly unlikely. The X-ray flares are rare and fleeting, making them difficult to pin down. Finding one of these intermediate black holes would be a monumental breakthrough. It would solve a fundamental cosmic classification problem, finally filling the gap between the small and the supermassive. More importantly, it could reveal how the giant black holes in the centers of galaxies first got their start. Did they grow from these very seeds, these intermediate mass black holes that formed in the dense environments of ancient star clusters? The hunt continues, a high-stakes detective story written in the frantic orbits of stars and the ghostly flicker of high-energy light. What other invisible giants are we walking past, hidden in plain sight within the glittering crowds of these stellar metropolises? The hunt for invisible giants is complicated by an even more fundamental mystery, one written in the very chemistry of the stars themselves. For generations, astronomers held a simple, elegant belief about globular clusters. They were thought to be perfect fossils, each one a single, simultaneous burst of star formation from a pristine cloud of hydrogen and helium. Every star in a given cluster, we assumed, was a chemical twin, born from the same material at the same cosmic instant. This belief has been utterly shattered. We now know that many of these ancient clusters are not simple, one-generation families. They are complex stellar societies with multiple, distinct populations of stars, each with its own unique chemical fingerprint. This discovery is as shocking as an archaeologist finding a modern smartphone buried inside a pharaoh's tomb. The evidence is found by dissecting the light from individual stars with extreme precision. Within a single, seemingly uniform cluster, we find one group of stars with the expected primordial composition. But then we find a second, and sometimes even a third generation of stars that are chemically enriched. They contain significantly higher amounts of elements like nitrogen, sodium, and aluminum. These heavier elements could only have been forged in the nuclear furnaces of the first generation of massive stars and then scattered into the cluster's gas when those stars exploded as supernova. This means a second wave of stars had to form from this polluted, enriched material. But here lies the monumental problem. The energy released by those first supernova is so immense that it should have violently blown all the remaining gas clear out of the cluster's feeble gravitational grasp. With no gas left, there could be no second generation. The cluster should have been left with only its first and final batch of stars, yet the multiple populations are undeniably there. How did these clusters hold onto enough gas to form new stars against the titanic force of their own supernova? This single observation has overturned our entire understanding of how these cosmic cities are built. It forces us to consider that the early lives of globular clusters were far more turbulent and chaotic than we ever dreamed, with gas swirling and collapsing in ways we are only beginning to model. The very existence of these multiple generations suggests a resilience, a stubborn ability to recycle and renew, that makes these ancient clusters feel less like fossils and more like living, breathing entities. If our most basic assumption about their birth was wrong, what other foundational truths are we only just beginning to see? This chemical rebellion within stellar populations forces us to look beyond our own galaxy for answers. And in our nearest galactic neighbor, Andromeda, astronomers have found something that shatters the fossil metaphor entirely. We have always linked globular clusters with the dawn of time, viewing them as exclusive relics of the universe's violent infancy. But Andromeda hosts clusters that are shockingly, undeniably young. Some are just a few 100 million years old, mere infants compared to the 13-billion-year-old elders we are used to. How can such a thing exist? Our own Milky Way seems to have stopped forming these dense stellar cities long ago, as if the recipe was lost to cosmic history. Yet in Andromeda, the factory is apparently still open. The discovery of these youthful assemblies suggests that the process of creating a globular cluster is not a one-time event locked in the distant past. It is an ongoing cosmic capability. The birth of these young clusters is tied to Andromeda's more active and violent recent history. They likely formed from the immense shockwaves and compression of gas triggered by galactic collisions and mergers. When galaxies interact, their gravitational dance doesn't just tear stars apart. It can also trigger furious bursts of new star formation, compassing gas clouds so violently that they collapse directly into these incredibly dense, massive clusters. This means globular clusters are not just fossils, they are also living proof of a galaxy's dynamic life, born from both the primordial universe and from contemporary cosmic car crashes. Their existence in Andromeda raises a profound question about our own home. Has the Milky Way simply been quieter, lacking the recent major mergers needed to spark a new generation of clusters? Or have we been looking in the wrong places, missing a population of younger clusters hiding in plain sight? The discovery expands the life story of these stellar cities, proving that their formation is a story that is still being written. What other fundamental rules about our cosmos are merely reflections of our own limited galactic backyard? The same violent dynamics that forge blue stragglers can also tear families apart with unimaginable force. In the chaotic core of a dense star cluster, a close gravitational encounter between three or more stars can act as a cosmic slingshot. One star is often flung outward at a speed so tremendous it can break free not only from its cluster but from the entire galaxy's gravitational grasp. These are the hypervelocity stars, and they are some of the fastest solitary objects we have ever witnessed, racing through the void at millions of miles per hour. Imagine a star, a sphere of incandescent plasma larger than our own sun, being ejected from its home like a bullet from a gun. It becomes a permanent exile, destined to cross the intergalactic darkness alone, its light a solitary beacon in an ocean of nothing. The discovery of these stellar runaways fundamentally changed our understanding of a star cluster's influence. We once saw them as closed, insular communities, but they are also powerful accelerators, capable of flinging their own members into the great beyond. This process acts as a form of gravitational evaporation, slowly bleeding stars from the cluster over billions of years and shaping its long-term evolution. Each hypervelocity star we detect is a fossil record of a violent encounter that occurred long ago in a crowded stellar city. Their trajectories are clues pointing back to the chaotic hearts of the clusters they once called home. What other cosmic projectiles have we missed, their stories written in speed and solitude as they journey between the galaxies? These stellar chemical fingerprints reveal a cosmos far more complex than we ever imagined. The very elements that make up the stars within a single, ancient cluster are not uniform. From one star to the next, we find bizarre and dramatic variations in the amounts of light elements like helium, sodium, and oxygen. This is the multiple population phenomenon, and it represents one of the most significant unsolved problems in all of astrophysics today. We are not looking at a simple family of chemical twins. We are looking at a diverse stellar society with a deeply puzzling history. The most straightforward explanation points to the first generation of massive stars. When these giants ended their lives in supernova explosions, they would have seeded the cluster's remaining gas with new, heavier elements. A second generation of stars could then form from this enriched material, naturally explaining why they would have different chemical signatures than their predecessors. But the physics of this process presents a monumental roadblock. The sheer energy unleashed by those first supernovas should have been catastrophic. It should have acted like a cosmic hurricane, blasting every last wisp of leftover gas out of the cluster forever. With no gas reservoir left, the formation of a second generation of stars would have been impossible. The cluster should have been a one-and-done event. Yet, the multiple populations are undeniably there, staring back at us from our telescopes. How did these clusters manage to hold onto their gas against such a violent purge? One compelling theory suggests the first generation of stars might not have all been supernova progenitors. Perhaps many of them were instead slower burning, intermediate mass stars known as asymptotic giant branch stars. These stars do not explode. Instead, they gently blow their enriched outer layers away in powerful but less destructive stellar winds. This would be like a gentle, persistent rain of new elements falling back into the cluster's core, rather than a single, shattering blast. This polluted gas could then coalesce into a new wave of stars without being completely lost to intergalactic space. Another, more radical idea proposes that the second generation formed from gas that was actually accreted from outside the cluster, stolen from the surrounding galaxy during a close passage. But this, too, has its own set of challenges, requiring a very specific and delicate set of gravitational conditions. The truth is, we still do not have a single, universally accepted model that can explain the precise and strange patterns we see. Why is one star brimming with sodium but poor in oxygen, while its neighbor, born from the same gas cloud, shows the exact opposite pattern? The chemistry is a crime scene, and we are still piecing together how the enrichment happened when it happened, and how the gas survived long enough to create the stellar generations we see today. This is not just a minor puzzle. It strikes at the very heart of how these fundamental building blocks of galaxies are assembled and evolve. The multiple population problem forces us to rewrite the entire first chapter of a globular cluster's life, a chapter that was far more turbulent, complex, and resilient than the simple fossil story we once believed. The same violent dynamics that fling stars across the galaxy also forge the most powerful collisions in the cosmos. Deep within the crowded cores of globular clusters, a silent, invisible factory is constantly at work, producing binary pairs of black holes destined to merge. These are the events that ripple the very fabric of space-time, generating the gravitational waves our most sensitive observatories have just begun to detect. How does this factory operate? In the serene suburbs of the galaxy, where stars are widely spaced, a binary black hole system is a cosmic rarity. But inside a globular cluster, the environment is a gravitational pinball machine. When two black holes, each the remnant of a massive star, swing too close to one another, they can become gravitationally bound. They form a binary pair, a silent, dark dance in the heart of the stellar crowd. This dance, however, is rarely a peaceful one. The cluster's extreme density acts as a cosmic matchmaker. As other stars or black holes pass near this dark couple, their gravitational nudges repeatedly tighten the black hole's orbit. Over millions of years, the two black holes spiral closer and closer, stealing orbital energy from their surroundings and transferring it to passing stars, which are often flung out of the cluster entirely. This relentless process, called dynamical hardening, continues until the black holes are so close that they can no longer resist the inevitable. They begin to lose energy by radiating it away in the form of gravitational waves, faint ripples in spacetime predicted by Einstein. This emission seals their fate. Their final orbits become a death spiral, culminating in a collision that unleashes more power in a fraction of a second than all the stars in the observable universe combined. This is the event that facilities like LIGO and Virgo have captured. The chirp-like signal of a gravitational wave, rising in frequency and amplitude before ceasing abruptly, is the signature of two black holes becoming one. Many of the first black hole mergers we have detected are now thought to have originated in these dense stellar cities. The clusters provide the perfect conditions for these dark partnerships to form and tighten far more efficiently than they ever could in isolation. This redefines a star cluster's role in the cosmic cycle. They are not just museums of ancient stars, but active, violent engines, forging the most extreme objects in the universe and broadcasting their cataclysmic births across the cosmos as tremors in reality itself. What other invisible mergers are happening right now in these glittering cities, sending their silent signals across the void? Yet the violence of colliding black holes is not the only invisible force shaping these clusters. A deeper, more pervasive mystery hides within their gravitational fields, one that challenges our understanding of the universe's most elusive substance, dark matter. For decades, the scientific consensus was clear. Globular clusters, those ancient relics, were believed to be devoid of dark matter. Their immense gravity, we thought, was supplied entirely by the collective mass of their countless stars, with perhaps a contribution from stellar remnants like black holes and neutron stars. This made them simple, clean laboratories for studying pure stellar dynamics, but recent, precise measurements are casting a long shadow of doubt over this tidy picture. The evidence comes from carefully tracking the motions of stars, especially those in the cluster's outer regions. Just as the speed of planets reveals the sun's mass, the velocity of these distant stars reveals the total mass holding the cluster together. In several clusters, astronomers have found a startling discrepancy. The stars are moving too fast. Their speeds are greater than what can be explained by the gravitational pull of all the visible matter we can count. There seems to be extra mass there, a hidden source of gravity that we cannot see. This is the classic signature of dark matter, the invisible stuff that makes up most of the universe's mass. But its presence in a globular cluster would be revolutionary. It would mean these structures are not the simple stellar fossils we imagined. They would instead be embedded in their own massive, invisible halos of dark matter, fundamentally altering their origin story. The debate now raging among astronomers is intense. Could our mass measurements be wrong? Perhaps a large population of faint, nearly invisible stellar remnants like white dwarfs or neutron stars is hiding in the clusters, providing the extra gravity without the need for dark matter. Or maybe the complex gravitational interactions in a cluster's long life can produce these fast-moving stars through natural dynamics, creating only the illusion of missing mass. Each explanation faces its own hurdles. Finding enough faint remnants to account for the gravity is a challenge, and computer simulations of cluster evolution struggle to replicate the observed stellar speeds without adding some form of dark matter. If dark matter is indeed present, it rewrites the first chapter of a globular cluster's life. It suggests they were born within much larger, denser clouds of dark matter in the early universe, and that this dark matter scaffold was essential for their formation and survival. The clusters we see today would be just the luminous tip of a vast dark iceberg. This puzzle remains unsolved, a quiet tension between observation and theory. Are we looking at the first evidence of dark matter's role in the smallest stellar systems? Or is the universe once again revealing a new, unexpected layer of gravitational complexity? The answer is hidden in the subtle, frantic dance of stars on the edge of these ancient cities. The gravitational pull of our galaxy is slowly unraveling these ancient stellar cities. As globular clusters orbit the Milky Way, they are subjected to an immense and relentless force, the galactic tide. Just as the Moon's gravity stretches Earth's oceans, our galaxy's gravitational field tugs more strongly on the side of the cluster closest to the galactic center and less strongly on the far side. This difference in pull over billions of years stretches the cluster, pulling stars away from its main body. The result is a breathtaking cosmic phenomenon, vast and faint rivers of stars flowing through the darkness. These are tidal tails and stellar streams, and they are some of the most delicate and revealing structures in the entire sky. finding them is an immense challenge. These streams are so faint, so ethereal, that they are completely invisible to the naked eye and were lost in the background glow of the galaxy for centuries. Their discovery required sophisticated digital sky surveys and computer algorithms capable of filtering out the foreground of Milky Way stars to reveal the subtle, flowing patterns beneath. The most famous example is the tidal tails of the Palomar 5 cluster. This faint cluster is being methodically dismantled, its stars drawn out into two magnificent, opposing streams that stretch across an incredible 20 degrees of the night sky. These streams are not random debris. They are precise tracers, cosmic filaments that map the invisible gravitational landscape of our galaxy. By tracking the path of these stellar rivers, astronomers can literally see the distribution of dark matter, the unseen scaffolding that shapes the Milky Way. The stars in the stream act like breadcrumbs, marking the cluster's orbital path and revealing the subtle pulls and tugs of the galaxy's hidden mass. But these streams are more than just a map of the present, they are a chronicle of the past. The specific length and shape of a tidal tail tell a detailed story of the cluster's lifetime. They reveal how many close encounters the cluster has had with other massive objects, like giant molecular clouds or the galactic bulge, gravitational interactions that would have jolted the cluster and accelerated its dissolution. A long, smooth tail suggests a relatively peaceful orbital history. A tail that is kinked or shows gaps is evidence of a past collision, a gravitational shockwave that disrupted the stream. In this way, these faint trails of stars are a forensic record, allowing us to reconstruct billions of years of a cluster's journey through the galaxy. We see not just a cluster as it is today, but a timeline of its slow and inevitable destruction. This changes our perception of these objects from permanent monuments to transient, though long-lived, features of the galactic landscape. Every cluster we see is in a different stage of this process, some still tightly bound, others already stretched into ghostly ribbons across the heavens. What other ancient stories are written in these fading stellar signatures, waiting for us to learn how to read them? That search for dark matter's ghostly pull is challenged by a discovery that redefines the very nature of a star cluster. Far beyond the familiar stars of the Milky Way, in the small, cannibalized Sagittarius dwarf galaxy, lies the globular cluster M54. For a long time, it was considered just another one of these ancient stellar collections, albeit one orbiting our galaxy from a distance. But then, astronomers pointed their most powerful telescopes at its core and found something that should not exist there. They found the unmistakable, frantic motion of stars orbiting an invisible, monstrously heavy object. The velocities were so extreme that only one thing could explain them: a supermassive black hole. This was not the intermediate mass black hole we have been searching for. This was a genuine supermassive giant weighing in at several thousand solar masses. Its presence in a globular cluster is revolutionary. It blurs the line between what we call a star cluster and what we call a dwarf galaxy. The leading theory is that M54 is not truly the core of the Sagittarius dwarf galaxy itself. When our Milky Way began tearing that small galaxy apart, its central black hole may have been left behind, stranded within the cluster's dense stellar population. This means we might not be looking at a star cluster with a black hole, but at the stripped-down nucleus of a devoured galaxy, a ghostly heart beating within a stellar shell. The implications are staggering. If one globular cluster can harbor such a beast, how many others are actually the fossil cores of long-dead galaxies, their central monsters hidden in plain sight? This single object forces us to reconsider the ancestry of every massive cluster in our galactic halo. Are we living in a graveyard of galactic nuclei, each one masquerading as a simple ball of stars? Even the magnetic fields of these clusters hold a strange and unexpected story. When astronomers turned their radio telescopes toward these ancient stellar cities, they expected to find only the faint, chaotic magnetic signatures of individual stars. Instead, they discovered something far more organized, a large-scale magnetic field that seems to weave through the entire cluster itself. This is as surprising as finding a perfectly preserved ancient power grid still humming with energy beneath the ruins of a city abandoned for billions of years. How can such a fragile, structured force persist in such a violent and ancient environment? The constant gravitational jostling and stellar interactions should have shredded any organized magnetic field long ago. Yet the evidence is there, written in the polarization of radio waves emitted by the cluster. The origins of these fields are a subject of intense debate. One compelling theory suggests they are fossil fields, primordial magnetic lines of force that were trapped within the cluster's gas at the very moment of its formation. Think of it as a cosmic snapshot, a magnetic imprint from the cluster's violent birth that has somehow managed to survive against all odds, locked in place for over 10 billion years. Another possibility points to an ongoing dynamo effect. As the cluster spins, the collective motion of its ionized gas and countless stars could generate and sustain a magnetic field, much like the churning of molten iron in Earth's core generates our planet's magnetic field. This would mean the cluster is not a static fossil, but a dynamic engine, actively producing its own invisible force field even in its old age. The presence of these fields adds another layer of profound complexity to our understanding. It suggests that these structures are not just gravitationally bound collections of stars, but magnetized entities, where invisible lines of force may subtly influence the motion of gas, the paths of stars, and perhaps even the formation of those bizarre blue stragglers. What other invisible structures are woven through these glittering star cities, quietly shaping their destiny from within? The quiet cannibalism of galaxies has a smaller, more intimate counterpart among star clusters themselves. Far beyond our own Milky Way, astronomers have identified a pair of clusters locked in a cosmic drama named for the Greek Titan who devoured his own children, Kronos, and its companion, Krios. Kronos is a massive, ancient cluster, while Krios is its smaller, lighter neighbor. For billions of years, they have journeyed through space together, but their relationship is far from peaceful. Spectroscopic analysis of the stars within Kronos reveals a startling chemical schism. A significant portion of its stars possess a distinct elemental fingerprint, rich in specific metals that do not match the rest of the cluster's primordial population. This chemical signature is not native to Kronos. It is an alien imprint, a ghostly record of a long-term act of stellar consumption. The evidence points to a staggering conclusion. As the two clusters swung past each other in their shared orbit, the more massive Kronos used its superior gravity to violently strip stars away from the smaller Krios. Over eons, Kronos did not just steal stars, it digested them, incorporating these foreign bodies into its own structure until they became indistinguishable from the native population. The only trace left of this ancient act of cannibalism is the unique chemistry burned into the light of the stolen suns. This discovery transforms our view of clusters from isolated islands to interactive communities capable of preying on one another. It reveals a dynamic hierarchy of power in the cosmos, where even the largest and most stable stellar cities can grow by consuming their weaker neighbors. What other clusters in our sky are not pure families but cosmic chimeras, their glittering light a blend of multiple, long-vanished stellar communities? The chaos of stellar cannibalism is mirrored by the delicate orbital dances found deep within these clusters. Beyond lone rogue worlds, astronomers have spotted something even more improbable: entire planets orbiting not one but two stars at once. These circumbinary planets, which once sounded like pure science fiction, are enduring the gravitational storm of a globular cluster. The formation of such a system is a cosmic high-wire act. In the quiet solitude of deep space, a planet can form in a wide, stable disk of gas and dust swirling around a pair of newborn stars. But inside a star cluster, that process is under constant assault. The gentle gravitational pull from two parent stars is complicated by the violent, repeated yanks of 1,000 stellar neighbors passing far too close for comfort. Any nascent planetesimal trying to coalesce is likely to be hurled out of the system entirely, sent spiraling into the cold darkness between the stars. For a circumplanetary planet to survive here, it must form quickly and migrate into a perfectly stable orbit, a narrow gravitational sweet spot where the combined pull of the two stars creates a safe harbor. This orbit must be just right, far enough out to not be torn apart by the stellar duo's complex gravity, yet stable enough to resist being perturbed by passing stars for billions of years. Finding such a world in a cluster is like discovering a perfectly balanced spinning top still turning on the deck of a ship in a hurricane. Its very existence tells us that planet formation is an incredibly robust and tenacious process. These hardy worlds prove that even in the most tumultuous environments, the basic ingredients for solar systems can come together and cling to order against all odds. If planets can find stability orbiting two stars in a stellar mosh pit, then the potential for habitable worlds might be far greater and far stranger than we ever dared to believe. The ancient bulge at the heart of our Milky Way seemed to hold its own secrets until the cluster Terzan 5 revealed itself as a living relic. Nestled deep within the galactic core, this dense swarm of stars was long considered just another ancient globular cluster. But when astronomers finally pierced the thick dust clouds obscuring its light, they found a cosmic patchwork, a stellar archive containing not one, but at least two distinct populations of stars. These populations were separated by a staggering gulf of time and chemistry. One group was ancient, around 12 billion years old, and relatively poor in iron. The other was vastly younger, a mere 4.5 billion years old and brimming with iron. This was not a simple, single-birth family. It was a layered history book written in starlight. The presence of such different stellar generations, all bound together by gravity, is a profound clue. It suggests that Terzan 5 is not a true globular cluster in the classic sense. Instead, it is likely the fossilized core of a much larger primordial building block, a dwarf galaxy fragment that was devoured by the infant Milky Way. In this scenario, the older, iron-poor stars represent the original population of that captured dwarf. The younger, iron-rich generation then formed later from gas that was polluted by supernova from the first generation, gas that this massive structure was uniquely able to retain deep within the galaxy's gravitational well. This makes Terzan 5 a missing link, a surviving piece of the very construction material that assembled the galactic bulge itself. It is a time capsule from the era of galactic cannibalism, a silent witness to the violent mergers that built our cosmic home. If this one cluster is a fossilized galactic nucleus, how many other seemingly ordinary clusters are actually the hidden hearts of long-dead galaxies, their true identities still waiting to be uncovered? The stellar populations within these ancient clusters are hiding another quiet rebellion. Astronomers have noticed a strange demographic gap in some of these cosmic cities. When they count the stars, there is a distinct shortage of the brightest red giants, the swollen, elderly stars that should be shining with immense luminosity in their final stages of life. According to our most trusted models of stellar evolution, a predictable number of stars in any old cluster should reach this brilliant red giant phase. It is a standard, well-understood chapter in a star's life story, yet in certain clusters, the grandest and most luminous of these aging stars are simply not there. It is as if an entire generation of retired elders has mysteriously vanished from a bustling metropolis. Where did they go? The leading suspicion points to an unusually intense episode of mass loss. In the red giant phase, a star naturally puffs its outer layers away into space, eventually revealing its hot, dense core as a white dwarf. But in these clusters, the process may be far more violent and efficient. Perhaps the stars are shedding their mass in sudden, dramatic outbursts, or in a continuous, powerful wind that strips them down to their cores much faster than expected. This would cause them to bypass the brightest, most visible stage of their red giant life, transitioning almost directly from a normal giant to a faint white dwarf, effectively disappearing from our view. This missing red giant problem is more than a simple accounting error. It suggests that the internal physics of stars in these dense environments may be fundamentally different. Could the extreme crowding influence how a star ages, the collective gravitational field, or perhaps even the subtle chemical differences from the multiple populations, might be triggering a more rapid and final death for these stars? The quiet absence of these expected giants is a loud signal that we are still missing a crucial piece of the stellar life cycle, a piece that these ancient clusters are uniquely positioned to reveal. These ghostly halos of dark matter are not a universal feature of every star cluster. In fact, many of these ancient stellar cities, when subjected to the same precise measurements of stellar motion, show no such gravitational discrepancy at all. Their stars move at speeds that can be perfectly explained by the combined mass of all the visible suns, stellar remnants, and dust within them. This is precisely what the traditional model of cluster formation predicted. These clusters appear to be exactly what we long believed them to be, self-gravitating islands of pure stellar matter. Their clean, dark matter-free nature suggests they were born in a specific way, likely condensing from a single, massive cloud of pristine gas within the early galaxy's halo, without a significant dark matter scaffold to support them. This creates a deep and puzzling cosmic divide. Why do some clusters, like the spectacular Omega Centauri, show strong hints of that hidden gravitational pull, while countless others show none? It forces us to consider that we are not looking at a single, uniform class of object. The term globular cluster might be a cosmic umbrella sheltering two fundamentally different kinds of structures. One type is the simple, fossilized star cluster, born from a gas cloud and devoid of dark matter. The other might be something entirely different, the stripped-down corpse of a dwarf galaxy that once possessed its own massive dark matter halo. The clusters without dark matter reinforce our classic theories, providing a clean baseline for understanding stellar dynamics. But their existence, right alongside the mysterious outliers, deepens the overall enigma. It means the answer is not a simple yes or no. The true nature of a star cluster must be determined one by weighing its stars and listening to the silent testimony of their orbits. This duality challenges us to look closer, to find the subtle markers that distinguish a true cluster from a galactic ghost. These stellar puzzles are dwarfed by a signal from the depths of space, a burst of energy so intense it can outshine an entire galaxy for a few fleeting milliseconds. These are fast radio bursts, and their potential connection to star clusters adds another layer of profound mystery. For years after their discovery, the origin of these colossal, one-off blasts of radio waves was one of astronomy's greatest enigmas. They seemed to come from random points across the sky with no obvious source. Then, a breakthrough occurred. Astronomers managed to pinpoint the location of a repeating fast radio burst, and it led them directly to a surprising place, the outskirts of a galaxy with a known ancient globular cluster. This was a stunning revelation. Why would such an incredibly energetic event be linked to a stellar city thought to be populated by quiet, elderly stars? The prime suspect in this cosmic drama is a magnetar. Imagine the collapsed core of a dead star, a neutron star, but with a magnetic field so powerful it defies comprehension. A magnetar's magnetic field is 1,000 trillion times stronger than Earth's. If one were to come as close to our planet as the Moon, it would wipe the data from every credit card on the globe. In the dense core of a globular cluster, the conditions are perfect for creating these magnetic monsters. A magnetar could form from the collision of two neutron stars, or when a neutron star pulls enough material from a companion to collapse further into this ultramagnetic state. The theory is that a starquake on the surface of a magnetar, a sudden and catastrophic crustal shift, could release an immense amount of energy, twisting the magnetic field lines and unleashing a firestorm of radio waves across the universe. This single event would manifest to us as a fast radio burst. The fact that this might happen inside a globular cluster is revolutionary. It suggests these ancient assemblies are not just homes to stellar vampires and black hole factories, but also to these rare, hypermagnetic powerhouses capable of generating the most transient and brilliant flashes in the cosmos. The energy required is almost unimaginable, and the fact that a structure billions of years old can produce it tells us that the potential for violence within these clusters is far from spent. If a single starquake on a dead star can outshine a galaxy, what other incredible forces are we on the verge of discovering hidden within these ancient stellar metropolises? This intricate chain of stellar birth reveals itself not just in ancient relics, but in the vibrant nurseries of new star clusters. Far from being random splatters of star formation, some of the youngest clusters in our galaxy are arranged with an almost architectural precision. They form along vast, snaking filaments of cold, dark gas, appearing like a brilliant string of pearls against the velvet darkness of space. These cosmic filaments are the true skeletons of the galaxy, colossal structures light-years long that weave through giant molecular clouds. Gravity works relentlessly along these dense threads, causing them to fragment and contract at specific points. Each knot of gas, pinched off from the filament, collapses under its own weight to ignite a new star and often an entire small cluster of stars. This process creates a linear sequence of stellar groups, all born from the same cosmic umbilical cord and strung together across the void. This is not a gentle, isolated birth. The formation of these pearl-like clusters is often triggered by a violent external force. The shock wave from a nearby supernova explosion, or the intense radiation pressure from a family of massive newborn stars, can slam into a molecular cloud like a tidal wave. This immense pressure compresses the gas, causing it to collapse and flow along the paths of least resistance, which are these pre-existing filaments. A cloud does not collapse into a single, formless blob. Instead, it funnels its material into these dark rivers, seeding them with the conditions for synchronized stellar birth. Observing this string of pearls phenomenon has fundamentally changed our understanding of how star clusters are assembled. It shows us that their birth is an ordered, structured event, guided by the invisible architecture of interstellar gas. These aligned chains are a frozen moment in time, a snapshot of the very first chapter in the life of a star cluster, revealing that even in the chaos of creation, the cosmos has a hidden tendency toward elegant, linear design. What other patterns govern the birth of stars, waiting to be read in the light of these young, shining necklaces? The sheer number of stellar pairs in these clusters rewrites their entire social dynamic. While we often picture stars as solitary suns, many globular clusters are revealed to be bustling metropolises where binary systems are the rule, not the exception. In some of these ancient cities, the fraction of stars locked in gravitational partnerships is astonishingly high, far exceeding what we see in our own galactic neighborhood. This prevalence of stellar couples fundamentally alters the life and death of the entire cluster. A binary star system is a gravitational engine. The close dance between two stars acts as a reservoir of energy. When other stars pass nearby, the binary can trade gravitational energy with them in a complex cosmic exchange. This process does two things. It hardens the binary, pulling the two stars closer together in a tighter, faster orbit. Simultaneously, it gives the single passing star a gravitational kick, often flinging it out into the cluster's outskirts or even ejecting it entirely into the galactic halo. Over billions of years, this relentless gravitational poker game, fueled by countless binary systems, slowly heats the cluster. It pushes lighter stars to the edges and allows the most massive systems to sink to the core, dramatically shaping the cluster's structure and accelerating its evolution. But the most dramatic consequences are reserved for the binary systems themselves. As these pairs harden, their orbits can become incredibly intimate. If one star evolves into a giant and swells, its outer layers can be siphoned directly onto its companion. When that companion is a dense stellar corpse like a neutron star or a black hole, the stolen gas doesn't just accumulate. It spirals in at near light speed, heating to millions of degrees and unleashing a torrent of X-rays. This is how we get X-ray binaries, some of the most powerful and exotic objects in the cluster. We see them as brilliant, flickering beacons of high-energy light, the direct result of a binary relationship turned predatory. These systems are not just cosmic oddities. They are the direct offspring of the cluster's crowded social life. The high binary fraction essentially seeds the environment with the potential for such violent and energetic interactions. It means that the exotic phenomena we observe, from X-ray bursts to the eventual collisions of black holes, are not random accidents. They are the inevitable products of a society built on stellar partnerships, where gravity forces stars into dances that often end in spectacular, violent finales. The silent, spinning heart of a millisecond pulsar should be a cosmic lighthouse. These rapidly rotating neutron stars, spun up by siphoning material from a companion, typically flash brilliant, regular pulses of radio waves across the galaxy. But in the dense cores of globular clusters, astronomers are finding pulsars that break this fundamental rule. They are the quiet millisecond pulsars, objects that spin hundreds of times per second yet remain stubbornly silent in the radio spectrum. Their lighthouse beams, it seems, are switched off. This silence is not an absence, however. When observed with X-ray and gamma-ray telescopes, these same pulsars blaze with intense, high-energy light. They are cosmic engines running in stealth mode, their most powerful emissions channeled into a part of the spectrum our eyes can never see. This bizarre disconnect challenges the very core of how we understand pulsar physics. The prevailing model suggests that a pulsar's intense magnetic fields generate radiation across multiple wavelengths, with the radio pulses being a fundamental, inseparable part of the package. The existence of these radio-silent but gamma-ray-loud pulsars shatters that assumption. It implies that the emission mechanisms for radio waves and high-energy light are not as tightly linked as we thought. Something in the extreme environment of a globular cluster is allowing these pulsars to operate differently. Perhaps the process of mass transfer from their companion stars is altering their magnetic fields in a unique way, suppressing the radio emission while amplifying the gamma-ray output. Or maybe the sheer density of stellar neighbors creates a fog of ionized gas that absorbs or scatters the radio waves before they can escape the cluster, while the more penetrating gamma rays stream through unimpeded. These quiet pulsars force us to reconsider the entire life cycle of these spinning stellar corpses. They are not just faster versions of ordinary pulsars, they are a distinct and mysterious breed, their true nature revealed only when we look at the universe through the most energetic lenses. What other silent sentinels are hiding in these crowded stellar cities? Their stories told not in radio whispers but in the violent scream of gamma rays. Even the quiet, cooling death of a star can be twisted into something unexpected within these dense stellar cities. White dwarfs are the final, fading embers of sun-like stars, Earth-sized spheres of degenerate matter so dense that a single teaspoon would weigh more than an elephant. For the vast majority of these stellar corpses, the story is simple and predictable. After a star exhausts its hydrogen fuel, it burns helium in its core, fusing it into carbon and oxygen. When the fuel is gone, it sheds its outer layers and leaves behind a dense, hot core composed primarily of carbon and oxygen. This is the standard white dwarf we expect to find everywhere. But in the ancient populations of globular clusters, astronomers have found a population of white dwarfs that defy this textbook ending. These white dwarfs are not made of carbon and oxygen. Their cores are composed almost entirely of helium. This discovery is as perplexing as finding a perfectly preserved skeleton that, upon examination, is missing its entire spinal column. How can a star die without ever creating the heavy elements that are the hallmark of its final nuclear burning phase? The answer appears to lie not in the solitary death of a star, but in the violent social dynamics of the cluster itself. A helium-core white dwarf is a star that died young, its life cut short before it could reach its natural conclusion. In the crowded core, a sun-like star orbiting in a tight binary system can have its evolution dramatically accelerated. As the star begins to swell into a red giant, its outer hydrogen-rich layers become gravitationally vulnerable. Its more evolved companion, which could be another white dwarf or a neutron star, acts as a stellar vampire. It begins to siphon this hydrogen envelope away, pulling the material onto itself. This process strips the red giant down to its bare core long before that core has had a chance to ignite its helium and begin fusing it into carbon and oxygen. What remains is a hot, exposed core of helium, a stellar embryo that never got to grow up. This object then quickly cools, becoming a white dwarf with a composition that reveals a violent and premature death. These helium-core white dwarfs are therefore not natural endpoints but cosmic accidents. They are the stripped, naked remains of stars that were robbed of their outer layers and their nuclear destiny. Their existence is a direct testament to the frequency and intensity of stellar interactions in these crowded environments. They are the ghosts of stellar encounters, their very chemistry a permanent record of a long-ago gravitational theft. If the quiet death of a star can be so dramatically altered, what other fundamental life cycles are being rewritten in the bustling cores of these ancient cities? The quiet death of a star can be rewritten by its social environment, but the very identity of a stellar city can also be a cosmic lie. Lilla 1 has long been catalogued as just another globular cluster, a dense ball of ancient stars huddled near the galactic bulge. But newer, sharper observations have peeled back its layers to reveal a startling duality. This object is a cosmic chimera, possessing the key characteristics of both a globular cluster and the nucleus of a dwarf galaxy. The first clue lies in its stellar population. Unlike the relatively simple, ancient stars of a classic globular, Lilla 1 contains a complex mix. It holds a very old population, but also a significantly younger one, with stars just a few billion years old. This spread of ages is a hallmark of a galaxy which can form stars in multiple episodes over vast cosmic timescales, not a single birth cluster. Then there is the metal content. The stars in Lilla 1 show a wide range of metallicities, meaning some are rich in heavy elements while others are poor. This is exactly what you would expect from a galaxy that has been progressively enriching its gas with each generation of supernova. A traditional globular cluster, by contrast, should have stars of a much more uniform chemical composition. The most compelling evidence, however, may be its sheer mass and density. Lilla 1 is extraordinarily massive and packed with stars, pushing it into a regime that overlaps with the very smallest galactic nuclei. It sits in a strange middle ground, too massive and complex to be a simple cluster, yet too small to be classified as a full-fledged galaxy. This dual identity forces a profound reclassification. Lilla 1 is likely the stripped core of a dwarf galaxy that was devoured by the Milky Way long ago. Its outer stars were torn away and scattered into the galactic halo, leaving behind only its resilient, densely packed heart. What we see today is a ghost, the fossilized central engine of a galaxy that no longer exists, masquerading for eons as a simple star cluster. If Lilla 1 is a galactic nucleus in disguise, how many other clusters in our sky are living under similar false pretenses, their true cosmic ancestry hidden behind a veil of glittering stars? Even the oldest and quietest star clusters can be given a new lease on life. We label some of these ancient assemblies as red and dead, filled with cool, elderly stars and devoid of the gas needed to spark any new stellar birth. They are cosmic retirement communities, their days of vibrant creation long behind them, yet a remarkable process can shatter this peaceful senescence. When one of these dormant clusters has a chance encounter with a giant molecular cloud, a sprawling nursery of cold gas and dust light years across, a cosmic rebirth can occur. The cluster, with its immense collective gravity, plows into this vast, diffuse cloud. It is not a gentle meeting. The gravitational shockwave from the cluster's passage compresses the cloud's gas, triggering violent instabilities within it. Just as a hand squeezing a balloon will cause certain sections to bulge and pop, the cloud collapses at its densest points. From this chaos, new stars ignite. This is not the slow, steady formation we see in isolated nebulae. This is a starburst, a sudden and brilliant wave of new suns flaring to life within the body of the ancient cluster itself. Astronomers see the evidence for this in clusters that display two distinct, widely separated ages of stars. One population is ancient, perhaps 12 billion years old. The other is shockingly young, sometimes just a few 100 million years old. The only way to explain such a stark generational divide is a dramatic infusion of fresh gas long after the cluster's initial formation. The old cluster acts as a cosmic seed, its gravity a catalyst that transforms a passing cloud into a new generation of stellar children. This process was thought to be incredibly rare, a cosmic fluke. But its very existence proves that no stellar city is ever truly dead. Given the right conditions and a fortunate collision, even the most ancient fossils in our galaxy can experience a sudden, violent, and brilliant spring. Even the most familiar stars can suddenly begin to behave in deeply unsettling ways. The red supergiant Betelgeuse, a brilliant shoulder in the constellation Orion, captivated the world when it dramatically faded in late 2019. For a few months, its light waned by over 60%, a change so stark it was visible to the naked eye. The astronomical community buzzed with a thrilling, if unnerving, possibility. Was this a prelude to a supernova? Was Betelgeuse about to explode? While the star eventually recovered its brightness, the event left a profound question hanging in the air. What cosmic process could cause such a massive, stable star to nearly vanish from the sky? The answer appears to be a combination of factors. Immense clouds of dust condensing from material the star itself had ejected, likely drifted in front of it, blocking its light. At the same time, the star's own surface was pulsating, a natural rhythm of expansion and contraction that cooled its outer layers and contributed to the dimming. This was not a singular freak event. We are now witnessing similar, enigmatic dimming in the ancient stars of globular clusters. These old red giants, distant cousins to Betelgeuse, are also experiencing sudden, sharp drops in brightness. In the crowded stellar cities, the explanations become even more complex. Could these cluster stars also be shrouding themselves in their own cosmic soot? Or does the dense environment introduce a new variable? One compelling theory suggests that in a cluster, a star's dimming might be triggered by a close gravitational encounter with another star or a binary system. Such a flyby could destabilize the giant star's outer layers, triggering a massive outburst of material that quickly condenses into a vast, opaque dust cloud. Alternatively, the complex internal chemistry of these cluster stars, a relic of the multiple population phenomenon, might make them more prone to these violent pulsations and dust-producing eruptions. The great dimmings, both in our galactic neighborhood and in faraway clusters, teach us a humbling lesson. We are learning that the final chapters of a star's life are not always a quiet, predictable fade-out. They can be dramatic, chaotic, and punctuated by episodes of self-obscuration, where a star literally hides itself behind a veil of its own making. If this is how giant stars behave before their final death, how many other cosmic farewells have we misunderstood simply because we were not watching closely enough? Perhaps no single object in our sky better embodies the mystery of star clusters than the colossal Omega Centauri. Shining as a faint, fuzzy patch to the naked eye, this giant has long been considered the king of our galaxy's globular clusters. But its true nature is far grander and more violent than that simple title suggests. The first clue lies in its sheer, staggering scale. Omega Centauri contains millions of stars, vastly outnumbering any other cluster in the Milky Way. Its gravitational pull is so immense that it holds itself together in a sphere nearly 150 light-years across. Yet, size alone was not the giveaway. When astronomers began to study its stars in detail, they found a level of chemical chaos that defied all the rules for a normal cluster. Instead of a single, uniform population of chemical twins, Omega Centauri stars are a wildly diverse family. They range from extremely metal-poor, ancient suns to stars rich in heavier elements, indicating multiple, distinct epochs of star formation spread over billions of years. This is not the signature of a single, collapsing gas cloud. This is the fingerprint of a galaxy, a system that lived long enough to recycle its gas through many generations of stars. The most compelling evidence, however, comes from the frantic motion of stars at its very heart. Their orbits are so fast and complex that they point to a single, terrifying conclusion: the presence of a central black hole of immense proportions. This is not the intermediate mass black hole we hunt for in other clusters. This is a genuine supermassive black hole with a mass estimated at tens of thousands of times that of our Sun. Such a monster could only form and be sustained at the center of a galaxy. The story that emerges is one of cosmic cannibalism. Omega Centauri is now widely believed to be the ravaged heart of a dwarf galaxy that ventured too close to the Milky Way in the distant past. Our galaxy's immense gravity acted like a cosmic thresher, violently stripping away the dwarf galaxy's outer stars over eons. All that remains is its densely packed, resilient core, a ghost of a galaxy that now orbits the very power that destroyed it. This reclassification solves many puzzles, but it opens a deeper one. If Omega Centauri is a galactic nucleus in disguise, then it forces us to look at every other massive cluster with suspicion. How many of the glittering balls of light in our halo are not true clusters at all, but the fossilized hearts of galaxies we consumed long ago? Even the faintest embers in these stellar cities hold a profound mystery. Astronomers have now mapped a hidden population of cosmic ghosts drifting through star clusters, objects known as brown dwarfs. These are the failed stars of the universe, too massive to be considered planets, yet not massive enough to ignite the sustained nuclear fusion that makes a true star shine. They form like stars from collapsing clouds of gas, but they never quite reach the critical mass to turn on. Instead, they spend their existence as dim, cooling cinders, fading slowly into darkness. What is so startling is not just their presence, but their sheer numbers and their solitude. We are finding them in clusters as free-floating objects, completely untethered to any parent star. This presents a serious challenge to our models of how stars and planets are born. In our own solar neighborhood, brown dwarfs are often found orbiting stars or drifting alone. But inside the intense gravitational pressure cooker of a star cluster, we expected a different story. The dominant theory of planet formation, called core accretion, suggests that planets, and by extension brown dwarfs that form like planets, build up slowly from dust grains within a disk swirling around a young star. In a cluster, that process should be constantly disrupted. The gravitational pull from passing stars should rip these delicate disks apart, scattering the material and preventing the slow, steady growth needed to form a substantial object like a brown dwarf. The fact that we see so many of them freely floating and not bound to any star suggests they must have formed in a different, faster way. Perhaps they collapsed directly from the primordial gas cloud of the cluster itself, just like proper stars, but simply ended up on the lower end of the mass scale. Yet if that is the case, why does the star formation process in clusters seem to produce such an overabundance of these failures? It is as if a factory designed to build brilliant suns has a bizarrely high rate of producing objects that never quite turn on. Their faint glow is a quiet rebellion, forcing us to reconsider the very boundary between a star and a planet, and challenging our understanding of how cosmic bodies are born in the most extreme of nurseries. This very expansion of the universe is now the source of one of cosmology's greatest crises, and star clusters are at the heart of the conflict. We are facing a fundamental disagreement over the speed at which the cosmos is growing, a problem known as the Hubble tension. On one side, we have meticulous measurements of the cosmic microwave background, the faint afterglow of the Big Bang. This primordial light allows us to calculate the universe's expansion rate, a value called the Hubble constant, with incredible precision. This method gives us one specific number. On the other side, astronomers use what they call the cosmic distance ladder, a step-by-step method to measure how fast galaxies are moving away from us. They use pulsating stars known as Cepheid variables and, crucially, specific types of supernova in distant galaxies to gauge distances and velocities. This entirely independent method yields a Hubble constant that is consistently, undeniably faster. The results do not match. It is as if two of the world's most accurate clocks, built on different principles, began ticking at different rates. This is not a small statistical fluke. It is a glaring discrepancy that threatens to unravel our standard model of cosmology. Where do star clusters fit into this high-stakes debate? They provide a crucial, independent rung on the cosmic distance ladder, a way to cross-check the measurements and see where the problem might lie. By studying the properties of stars at the main sequence turnoff in the oldest globular clusters, we can get a firm handle on their distances. These clusters act as anchor points, their well-understood stellar physics giving us a solid foundation from which to calibrate the distances to farther galaxies. When we use clusters in this way, their measurements often lean toward the faster expansion rate found with supernova. This independent confirmation from such ancient objects makes the tension even more acute and real. It tells us the problem is not with one single instrument or technique, but points to something deeper. Perhaps our understanding of the early universe's physics is incomplete, or maybe there is an unknown form of energy that began acting more recently, giving the expansion an extra push. The serene, ancient light of these star clusters is now illuminating a crack in the very foundation of modern physics, forcing us to ask a terrifying and thrilling question. Is our entire cosmic recipe the precise blend of dark matter and dark energy we thought we understood, missing a key ingredient? From pulsars that devour their neighbors to planets that orbit twin suns in stellar mosh pits, these 30 discoveries have systematically dismantled our placid vision of star clusters. They are not the simple, static fossils we once catalogued in our textbooks. Each revelation, from the chemical chaos of multiple populations to the invisible tug of dark matter and the violent factories of merging black holes, paints a far more dynamic portrait. These ancient stellar cities are cosmic pressure cookers and gravitational laboratories where the most extreme physics in the universe is not just theoretical but actively unfolding. They are places where stars cheat death, where galaxies hide their cannibalized hearts, and where the very fabric of space-time is constantly rippled by invisible collisions. The sheer breadth of these enigmas proves that our understanding of the cosmos is not nearly complete. The next generation of observatories, like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope, are already turning their powerful gaze toward these mysteries. With their unprecedented vision, we will peer into the crowded hearts of these clusters, weigh their invisible black holes, and finally decode the chemical crime scenes of their birth. The next great revelations are waiting, hidden in the light of a billion ancient suns. Tell us in the comments which of these strange discoveries reshaped your view of the cosmos the most.